It's a pleasure to inform you about the activities that we do in the Composites lab and about the activities maybe more in general as well. And I think I feel that this is it's nice the more people knows about this and may have an interest and then know how to proceed to engage with us and get access to the lab. So I will say something about that as well. I think it's a very important aspect of the activities that we actually make it available. What is available should be available to people across Chalmers. And who am I then? I'm a professor here at the Department of Industrial and Materials Science. I'm a professor in lightweight composite materials and structures. And I'm also the co-director for the area of advanced materials science, where the director is Maria Abrahamsson in chemistry. I'm also an editor for Composite Science Technology, which is the most important, I would say, composites journal in the world. And it's published by Elsevier. I also used to be the president for the International Committee and for the European Society of Composite Materials. So I've been active in composites research ever since I started my career as a scientist. And I've been with Chalmers for 6 years now. And just to set things in perspective, so the lab and my own activities are, as I said, within industrial materials science. And you know we have 6 divisions, and these numbers that I showed to the right are from 2018, so of course they changed a bit over time, and with EIB also, I guess they will go down a bit when it comes to turnover and so on. But we have six divisions working from users' need to form and function, materials and production. So we are quite a traditional mech-eng department, but perhaps lacking some of the fluid mechanics that you usually see there. So together with them too, I guess that we are covering the aspects of mechanical engineering. But our division also teaches quite a lot in civil engineering. And we are active in material science, production, nanoscience and nanotechnology, transport, with different type of cross-cutting activities, particularly via the areas of advance or the excellence initiatives. So this is the division, and the numbers you can see to your right here. So about 200 employees. And the division I work at is the material and computational mechanics. And what do we do then? We work in 5 different research areas, of which lightweight materials and structures is one. This is where I'm responsible for this activity, and it's mainly focusing on composite materials and mainly carbon fiber composites. But of course we also have process modeling and simulation, which is also then the manufacturing part of the composite is actually handled there. So, and I will say this again later, but we make our material when we make our final product. This is quite unique. If you compare to sheet metal, for instance, when you press sheet metal into a body in white for a car, for instance, then of course the material is available beforehand. So here we actually make our material at the same time as we make our products. We need to have both these activities. Then we have other areas, structural mechanics, which is mainly with the people at ACE. Multi-phase materials is you can think about hard metals and hard ceramics for cutting tools and stuff like that. And railway mechanics, those are the areas that we actually span over. And if we look at the research activities that we have on composites, we have focused quite heavily on transport applications, composites for transport applications, and we focus to develop, to facilitate development of energy efficient, lightweight vehicles across transport modes, you can say. And this is illustrating here some activities that we have. So Marcus Fagerström is working a lot on crash modeling. And he also works on different type of composites, like 3D woven composites for these type of applications. This is quite extensive progressive damage modeling that is needed for handling a crash simulation like this. I work also a lot on making efficient design methods for composites. So typically we have to do a lot of testing when we want to have a composite structure in aircraft to fly. And this is very, very costly. So we would like to replace some of the costly experimental work with cheaper analysis work. So we're trying to change this Rochot test pyramid, as we call it, with increased analysis abilities and efforts. And another thing which is actually taking most of my time nowadays is working on multifunctional composites. So we try to make something we call a structural battery, illustrated here as the body in white and the wheels of a car being not only structural materials but also actually storing electrical energy. So what are composites then? I think that it's important to know the functionalities of the different constituents, but formally, a composite material is a material consisting of at least two phases, and these two phases should interact in a way that they actually perform better than the single phase individually. And we typically talk about fibre-reinforced composites. We have glass or carbon fibers soaked into a resin, a molten polymer, or a monomer mix, which is then reacting and curing and forming a thermoset polymer. And the role of the fiber is, of course, to carry the load, is stiff and strong, and the matrix transfers loads between fibers and also stabilizes fibers. So if you think about a shoelace or a textile, it's very possible to pull that and you can feel a stiff response. But if you compress it, of course, you can't take any load. But having the matrix around the fibers, then suddenly this becomes stiff and strong as the sheet metal, for instance. So that's the role of the matrix. And of course, also the matrix is in many ways protecting the fibers. In particular, glass fibers are very sensitive to moisture, so the polymer is protecting them and keeps the performance well. And actually, if one is clever and use good combinations of materials, a composite material with the high volume fractions of fiber can have up to 5 times higher specific stiffness and strength than steel and aluminum. So you can think about making really lightweight materials with this technique. And there are different type of fiber architectures, and obviously, if one is moving from this very organized situation into a random fiber distribution or into a 3D woven reinforcement, then you lose properties in some way. And I illustrate that in this picture. So if you have very highly unidirectional oriented fibers with high volume fractions, you can have this 5 times the strength per kilogram for this compared to steel or aluminum. But if you suddenly decide that you want to have fibers in different directions, and you need that because these composites are very strong in this direction, but if you load them out of plane, then they're actually quite weak, even weaker than the polymer. So you need to put fibers in all directions where you have loads. And as you change this and add different directions, of course, the benefits are lost a bit. But there are, of course, this is what we look at when we try to introduce these composites, to find the optimal way of putting fibers, and this is actually the motivation and the guidance that we had. And if we need to take loads in some direction, we can even use embroidery and stuff like that to get fibers in the right positions. So we have many different manufacturing techniques available to us. What applications do we see today? We have automotive. They're quite interested in this nowadays. Sports equipment, of course, has been there. Windmills, these blades are becoming so long now that they actually not to bend so much in service that they hit the tower. They need to be made in carbon fiber composites nowadays. Aircraft has been for long, and we can see in construction work and in ships. And some statements made. So, well, of course, they are moving towards composites because they need to introduce them to reduce weight of the body in white for the future. And the Lufthansa made a statement that if they reduce the weight of their aircraft with 1 kilogram per aircraft, they will reduce the fuel consumption on their fleet by 30 tons per year. So you can see the immediate benefits of lightweight in these situations. And just showing the flexibility. This is an ice hockey player in the US, Canada actually. You can see the flex of that stick. So this is actually propelling the puck as it releases from the ice. So that's the modern way of doing a slap shot. But more interesting perhaps is the wing test of the Boeing aircraft. You can see how highly they flex these wings. So when you fly, you can see the wingtip vibrate a bit. It's not very dangerous, and it has been considered and tested at much greater extension. So this is a very flexible material that we can use. And manufacturing of this, as I said, we make the material at the same time as we make our product. And we have usually different steps to go through when we make the composite. And we need to consider these both in the manufacturing setup that we have in the lab, but also in the process simulation. The wetting of fibers, this is the matrix, and this is the fibers that are dry, that needs to be wetted by this flow front progressing into the material. And we're going to have voids there, so we need to consolidate, so we need to put pressure on to get this in a nice way. And then, of course, we need to put pressure on to form it in the shape that we want. And we must allow for excess resin to drain from the material. And also, we need to solidify if we do it by curing a monomer mix or if we do it by cooling a thermoplastic. Both things needs to be considered, because you actually build residual stresses in your material as you solidify your material. So these are issues that we work on in the team, and we have a lab now that allows us to make these materials. And this lab is located in the M building, and it's on the ground floor, and it's in the Yttre Labbhall. You can see here a picture as you enter this. You enter from the entrance 7B on Herzogsvägen, and here you have machine gren on this side, a bit to the left. You can see we have a manufacturing area and the trimming area, but we also have now the press and the oven out here. So we have expanded the facilities a bit since we integrated the lab. We opened the lab in late December, so 2 years ago, almost to the date. And it was opened by the Vice Presidents for Research and Education. And the reason for that Anders now I lost her name. That they opened this was that we actually shared the laboratory with Mia. We shared the laboratory between research and education. So not only are we using it for the research I presented, but also the students, in particular formula students and formula sailing, and some other teams are using the lab when they make composite structures. And I will go through the equipment that we have available in the lab, so you can have a site, and this is also presented on the website. I will give the link to the website in the end, so you can find information on your own later on. But it's a peculiar lab in the sense that we don't only have composite manufacturing facilities, we also have a facility that where we allow ourselves to work with these structural batteries. So we have a glove box, which is a dry and oxygen-free environment. And we can perform press forming, and we can do infusion techniques, and we can do tests in the glove box and outside the glove box. And of course we can trim and so on. I will go through this. So if we look at the traditional composites first, and we go with the multifunctional composites in a while, we have decided to go for press forming and resin infusion. I will tell you what that is. So press forming is pretty much what it sounds like. We make a stack of unconsolidated material, and we put that into a press in a press tool. This press you can see here. And that allows us to make quite complex shapes, but mainly volume fractions up to 50% or something of fibers. The other technique we use is resin infusion. Either we have one tool surface and we have a bag. So that's typically what we call the vacuum assisted resin infusion, or resin infusion on a flexible tool. Then we get one nice surface on the composite, and we can get high volume fractions up to 60%. But if we have two tool surfaces, then we call it resin transfer molding. Then we can get a very highly organized, high performance composite with 65% volume fraction of fibers. This is showing the Vari or rift type of technique, where we have a pump, sucking vacuum, and then actually we have a pot. This is also in evacuated, and we have the resin in there, and we suck in the resin, and the resin front is moving across the tool, and so we have dry fibers in this region, which is running through which are dry and are wetted by the monomer solution, and then we put this into an oven and cure it. So the press that we have is a very recent one. It actually was in use late October, so it's very new. It's good for, it's safe for students to work alone. We have it's a safety system that doesn't allow us to press when we have the door open and so on. We have about 30 centimeters of working space. We can go between room temperature and 250 degrees C, and we can do 600 by 600 millimeter plates that we can put in the tool. We can use these heaping plates directly, or we can have the tools there that we control. And we have lots of thermostats regulating the temperature, and we can also measure pressure in many positions. And it's a 300-ton press that we have. So it's quite versatile for most of the things we need to do. Of course, very big components are difficult to make here because you have this space that you need to consider. But it can be used to make plates and complex shaped composites, like a helmet for a worker or whatever. Then, if you look at the composite that we can make, this is the one composite that we have made where we have very thin polymer tape, fiber tapes. These are about 40 micrometers thick, or each of these tapes. It's actually one layer is only about 8 fibers on top of each other, but you can see that we can get very highly ordered composites in the press. The second technique I talked about was the vacuum infusion. For this we had this equipment, which is the vacuum pumps, the vacuum bags. We have bags, all you need for doing this. Of course, if you want to do something with a complex shape, you can do that. I will show some components from my students soon. You need to bring your own tool. And of course, for vacuum infusion, tools are very cheap. You can actually make a plug, and you can mill that with some kind of CNC equipment. I think that you can do it even at Chalmers if you have some polymer foam tools that you want to machine. So this is a very cheap technique to use and very versatile. So we have all the connections, all the stuff you need. We have 3 different pumps. We have a number of resin pots like this and so on that we can use. So we have a technician that can help you with this if you want to use this technique. And of course, the tools you need to make yourself, but you can go for RTM. We have 2 tool surfaces, or you can do this cheaper version with a flexible tool. So this is showing some examples. I believe this is actually not infusion because you have only an evacuation point here. So this is using pre-preg. And for pre-preg, it's basically a pre-impregnated dry fiber fabric that you have there. And you stack it similarly as you did for the resin infusion on a tool. In this case, you have one nice surface. This is the machined mold I told you about, and it can look different depending on what part you want to make. And if you have these pre-impregnated tapes, you can think about using vacuum just to evacuate them and cure them in the oven here, that's fine. But if you want to have really high volume fractions and very low void content, we usually use an autoclave. That's a pressurized oven. And for this, such an investment is very expensive. And if you want to have some dimensions, so you can make some. So if you want to make the monocoque for my student car, for instance, you need to have a quite long autoclave, and this is millions and millions of crowns to invest in such a tool. So actually, the students, when they make these pre-preg composites where they want to have very high quality, not relying on just the vacuum as he does in this case, they go to Aston Harald on Hönö, where they have a 5 meter long autoclave. They can go up to 6 bars and 400 degrees C. So that's a much more versatile tool. So we don't have that tool here in our lab, but we have it within our network. And you can see some of these pre-preg composite structures that they make, depending on the different components of the car they want to make. So here you have aluminum honeycomb to make a sandwich structure with. So this becomes very stiff in bending load. And then for this, of course, if you have infusion, then all of these honeycomb spaces will be filled with resin, so you don't want to use that. So you will use pre-preg instead here. This is some picture I got from the students where they make the monocoque, and this is then cured at Aston Harald on Höne. But it's nice that we have the students there. So from, I would say from early January until May, it's 24 hours a day there are students in our lab, more or less. They're not allowed to work on their own, they need to be there 2 and 2. And we have, of course, instructions on how to conduct and how to clean and so on. But it's nice that we have a lab that is heavily used. Okay, I don't know how we're on time. When we have made this component here, of course, there are regions that need to be trimmed. And if we cure them in our place, we have this large oven, which actually would fit this monocoque. So it's a 2 meter depth in the dimension, 1 meter wide, and 1.2 meters high. So the big oven is the one that was placed next to the press outside here. So it's actually behind the window here. You can't see it in this picture. And we also have a smaller oven because this is of course a lot of work and a lot of time to heat this up compared to if you have a small thing that you want to cure. We have a medium-sized oven in the trimming room, which is 80 by 80 by 80 centimeters. And that again can go up to 250 degrees C. We also have a small oven in the lab for curing these structural batteries, for instance, which is more a lab oven, but it's very, very precise in the temperatures and so on. We have diamond wet, so we need that when we want to trim surfaces, because edges, because the carbon fiber is very, very erosive. So any tool, any cutter that you use must be with diamond blade. We also have a drill, and we have a sander that we can actually sand these components afterwards. And this part of the lab, the cutting and trimming lab, is actually has a lower pressure than the surrounding room, so we don't get the dust to go out from this room. So if we then go to the multifunctional composites, this is the previous president of KTH. He's now interested in batteries as well. So he was here and tried our facilities. And here we have we show the energy area of advanced energy. We had their industrial advisory board, our activities on structural batteries. This is a bobbin with carbon fibers here. And we process all our structural batteries within this glove box. So this glove box is very nice in the performance when it comes to keeping a dry and oxygen-free environment. And we run things here, so we can use, if you have a problem where you want to use carbon black or carbon nanotubes or graphene, we can actually work with that in this glove box. Usually when you speak to the people in physics and so on, they are not very keen to have this type of materials in the glove box. Also we run thermosets in the glove box. It's a quite versatile tool for us. We have limited space. We have only 3 arms here, so 2 persons can work together. And the dimensions of the glove box is 1.5 meters times 75 times 90 centimeters. But more importantly, maybe the sluice, we can get things in which are in this dimension, 370 millimeters diameter and 600 millimeters long. If we make something bigger, we will not be able to get it out of the glove box. And of course, the good thing as well is that we can do characterization both for batteries and mechanical characterization inside the glove box. So for instance, we have a mechanical tensile tester that I will show you soon that runs in the glove box, and it's big like a matchbox. I just want to tell you something about the structural batteries that we work on and that we developed together with KTH and Imperial College. But this is a particular design that we have done together with KTH. We use carbon fibers as the negative electrodes. These are hosting lithium as well. So actually lithium ions are inserting the carbon fibers and coordinating with the carbon. And we are able to use them as electrodes for that reason. Also, they are very highly electron conductors. So we don't need to have a connector. We can actually just take out the electrons on one side. We separate this to a counter electrode, which is also carbon fibers, but those are coated with a positive electrode coating. So that's lithium iron phosphate typically in our case. And we separate them with a glass fiber separator or a polymer separator. and then we take out the electrons on the other side as well. And then we have a structured battery, a working one. So this one is storing electrical energy, but it can simultaneously carry mechanical load. And of course, then we need to characterize these materials. So we need to be able to characterize the electrochemical performance, the capacity, how much ions do we get in, how much energy can be stored. So we typically do galvanostatic or potassiostatic cycling of the batteries. And this is showing a galvanostatic cycling. We look for the capacity of the carbon fibers and the half cell only. And this is also important then, not only to have the capacity for the battery, but also we need to know how many cycles will this battery work. You know, if you buy a cell phone, maybe after 3 years, it doesn't stay charged very long. And this is because the capacity is reduced with time. And this is a measurement where we see how big retention we have in the battery. You can see this should approach 100%. If we are below 99%, of course, then this battery will decay very, very quickly. And this is showing quite promising results for this particular carbon fiber. And this we can do in the lab using a potentiostat or a battery cycler. This is the battery cycler, allowing us to run 10 batteries at the same time. 8 batteries. We have 8 channels for this one, for doing this cycling test that I showed. And this is also connected to the glove box, so we can do the tests inside the glove box or taking out the batteries in pouch bags and do it outside the glove box. The mechanical test I talked about, this is one of these carbon fiber reinforced structural batteries that I talked about, and in this case the fibers are oriented in the x-axis, and we have done tests with this match size tensile tester in the glove box, where we have recorded the force and the extension for this type of structural batteries for different layups and different separated materials and in different directions. So you can see you can do very low loads with this machine. So we can go up to 2000 Newton with this machine, but we can go down also to quite low. So it's a very nice equipment. And of course you can do tests also outside, but the good thing is that we have connections, so we can actually do it on open cells, so we don't need to protect them from oxygen or moisture. So if you have a small component and you want to do a test, of course you can do that also in this machine. And then we also make larger demonstrators. So here is just a very recent work. It's actually ongoing. We are going to present this for Airbus next week. This is a 300 by 15 300 by 15 centimeter. Yeah, so it's 3 decimeters by 1.5 decimeter. And they have 3 structured battery cells inside it. And we are making that. So we have carbon fiber composites on the outside. These are actually prepregs, and the glass fiber composite as well. And then we have the 3 structured batteries in their bags in this case. And we have the 3 bagged carbon fiber composites batteries in glass fiber composites here. So we have insulated these connectors. That's why we have the glass fiber composite, because the carbon fiber is connected, so you can't get this into contact with this, then you will get a short circuit. And then when we have built this, we actually can make electrochemical impedance spectroscopies to see how these cells work before and after, and how they work in service with time. So for this, of course, we need to make tests with the potentiostat that we use. We have, in our case, 4-channel Gamry. This is very expensive equipment, and it's of course desirable to have more channels. At the moment we only have 4, but we can do the more complicated tests like the EIS in this machine and do the battery cycling in the battery tester. And in this case we have these 3 cells at 9 volts then, and we use that to light up whatever. So this is actually a component which is intended for the personal supply unit on an aircraft. So you know the thing you have above your head when you fly, where you can get the fan, and you can get the lights on, and you can, in case of an emergency, you can also get the oxygen mask. Those are today powered in an aircraft with 2 cable systems. So 1 cable system which for the primary and 1 for the redundancy. And they think that they can use structured batteries for the backup, so they don't need to pull two very expensive cabling systems in there. So that's the purpose. And of course, we aim for 28 volt, but then we will need to have 10 battery cells in series, and we didn't manage that within this project. But the potentiostat is a very nice tool, and it can also then run inside the glove box. And when you plan your work, this is the manufacturing fabrication lab, that we call it, where we have the glove box and the infusion facilities and the preparation of the charge for your press and so on. But when you plan your work, you can actually sit on the top of that, on the roof of that lab, and have a run through with your students, so you can sit there and plan what you need to do, and then when you enter there, because there are often other people in the lab as well, you can do your stuff and do it right from the beginning and move to the press and so on. To be allowed to enter the lab, you need to take a course on thermoset polymers, handling of those, working with those. This is the REACH Directive, and is legislative. It's by law required that anyone working with these materials have taken this course. And this course is given by Chalmers centrally, and the contact is Mulitfunctional, and also there are regularly posted seminars, and this is the posting that is out now. So if you have a look, it's a half-a-day course, and it's quite interesting and helpful, I think, because most of these thermosets are allergenic, and it's very important that you don't get exposed to them in a way that you actually get a reaction, and they will help you to understand these issues. So you need to show a certificate that you're taking this course to be allowed to get the pass to the lab. That's basically it. And you can find more information on this website, and you can contact me or the technician Jan Möller. And if you have students, by the way, if you have students who want to have access, this course is for free. If you have scientists, researchers who want to get access, they have to pay for it. And also Brina is there, but she will leave at early on next year, so that will be me and Jan Möller who are available to help you. I think that's the end of the presentation, pretty much half an hour.